Yeah, welcome to a brand new episode of Power Systems. So, last two classes we saw first the single line diagram, how to make a single line diagram. Then we saw how the per unit calculations. If you have missed those videos, please you can go back to the videos. I'll be putting the link over there. If you are new to our channel, please like, share, and subscribe our channel. So this is about the transmission lines. As you could see from the previous class, what we have seen is regarding the transmission line. So in the representation, so I showed you a transmission line is basically predominantly inductive in nature, and it was represented by an inductance. So as far as the transmission line inductance is concerned, so how do we calculate the inductance of the transmission line? So in order to calculate the inductance of the transmission line and relate it to with different parameters and calculations and with different formats like your voltage regulation, efficiency, transmission line overall, power loss, and other factors. So we have to study about the internal and external inductance of the transmission line. So internal and external inductance of the transmission line. So how do we go about it? So let's start. So basically, the transmission line over here, the module would be, if you will see any transmission line, so it will not be a straight conductor. It is straight, but it has got a circular cross section. So it's like this, and the transmission line as such is not measured. It's measured it in mil. So basically, the conductor size, whenever you see some good foreign books, so it measures into 1 mil. So 1 mil is basically 1 in 10 power minus 3 inches. So this is 1 mil, whereas we have a one circular mill. This circular mill is 1.4 into pi into square mills. So this is what it means, a circular mill. And what is it? So if you do 1 by 4, so it would be 78.7845 in 10 power minus 6. So this is your one circular mill calculation. So now we are interested to understand the internal inductance of a transmission line and external inductance. So the total inductance of a transmission line that we'll find out would be the sum of the internal and the external inductances. To find out this basically, so what I have done is that I made a circle over there. I'll take a different red color over here. So I'll make one radius, okay, and so this is the external circle. Let's suppose this is the center, and I have this radius from here to here r, and I take a different color so that I draw one cross sectional area. So this is another circle. So my dotted, okay, I'll not draw dotted. Let me make a proper circle. Okay, one more circle I have drawn. So and then let's choose one more over here. Okay, so one more over here. Okay, so between these 2 points, let's suppose this is dx point, and from here to here, let's suppose this is x, and the current that is rotating in this, let this be ix. Okay, so what basically we are doing is we are considering a long circle. Actually, consider, okay, a long consider a um, a long circular conductor, obviously long round, okay, circular conductor with radius, as you can see, conductor with radius r, and it is carrying current ix, carrying current carrying current ix. So when we see this, there is a magnetic field that is getting induced inside the circle, okay, and let the magnetic field be hx around a circle of radius x. So let hx be the magnetic field, okay, magnetic field getting established inside the circle of radius x. So we know from the Ampere circuital law, the integral of magnetic field and the length over an area 0 to 2 pi x, because when you are establishing the entire circle, you will move 360-degree length, and if your entire length is 360 degree, and you cover an x distance, so this overall distance would be 0 to 2 pi will come for this 360 and x, so this would be equal to ix. Now if you this length hx will go outside, integral of dl will become L. Now we have 0 to 2 pi x, okay, is equal to ix. So this will become hx 2 pi x minus 0 is equal to ix. So you can safely write the equation. I will write with a different color final equation here. So you have from this equation hx would be equal to ix by 2 pi x. So this is basically the equation for the current that you are getting, that is hx is equal to ix by 2 pi x. So we can write this hx is equal to ix by 2 pi x. So and another, for now we have to go for the calculation of the internal inductance. Now if you have to go for the calculation of the internal inductance, what we do is that we obtain a simple expression. Simple expression is obtained. How is obtained? By what we will do is we will what we will do is that we will cover the internal flux linkages as obtained by covering the internal, okay, flux linkages. Basically it is all about electric engineering, is all about electromagnetism. Okay, so if you are new to my channel, so please subscribe it, like it. And what is electromagnetism is that all the electrical quantities, for example, can be represented into magnetic terms. Here I'll draw a table. For example, this is my electrical quantity, this is my magnetic quantity over here. Okay, so if in my electrical quantity I have voltage, here in my magnetic quantity, instead of voltage, what do I have? Instead of voltage, in case of a magnetic quantity, for voltage I'll be having, so suppose here I am having, yeah, let me draw this properly, okay, that you don't get, yeah, if I'm having voltage, okay, this is my electrical quantity, and this is my magnetic, so I'll have mmf. Okay, mmf. If I'm having current over here, I'll be having flux. If I'm having resistance over here, I'll be having reactance in the magnetic terms. So what I'm trying to convey to you is that I have this hx is equal to I by 2 pi x as such. So what I do is that I'll neglect the skin effect. Neglecting skin effect means basically, if you are new to this channel, skin effect, and new to the power system, so skin effect is a property of a material when we are of a conductor, especially if you are transferring the AC through it, it will have more resistance compared to a DC, because around the surface the resistance tries to become more. And in the few new lectures we'll be explaining you more about these other effects. And we have this preassumption and assuming uniform flux density, assuming uniform current. So we have to assume uniform current. So we can see throughout the conductor cross section. So throughout the conductor cross section. So as you see the conductor, so there is the surface of the conductor and overall dimension of the conductor. Suppose I is the current through the resistance. The earlier diagram wherein I have drawn this, yeah. So the earlier part of this was here. So not this one, this one, yeah. So here in the beginning, suppose this ix was through dx and I was the current that was going through this r. So in that case, so in this case, suppose yeah, so in this case what will happen? So in that case, so we can write our I by, this is the current by area I by pi r square, because uniform current density we have assumed. What we have done is that we are assuming uniform current density. So we uniform current density. So once we are assuming the uniform current density, that means that this current by area I by pi r square should be equal to Ix by pi x square. Okay, so from this equation, if we see this equation, we can write Ix is equal to pi x square into I divided by pi r square. So we get this pi cancel. In other terms, we can write Ix is equal to x square into I by r square. So also we saw that our hx was equal to what? Hx was equal to Ix by 2 pi x. So if this is equation 1 and let this be equation 2, from these two equations we can get a third equation, that is substituting Ix in 1 in 2. So we get hx is equal to, instead of ix sorry, hx is equal to x square into I r square into 1 by 2 pi x. So this x will vanish. So we have the new equation for this is hx would be equal to ix, okay, I into x, one quantity, divided by 2 pi r square. So 2 pi r square. So we have a new value for hx, that is ix divided by 2 pi r square. So for a non-magnetic conductor with constant permeability, mu naught, the magnetic flux density. So the magnetic flux density, that is your B naught, is equal to mu naught into hx. Okay. So this is the magnetic permeability that you are multiplying. So hx value you have, so you can write mu naught is equal to mu naught into I 2 pi r square into the x. Okay, so again, now that mu naught value you know, that is 4 pi and 10 power minus 7 Henry per meter. This is mu naught value is equal to 4 4 pi into 10 power minus 7 Henry per meter, where this is the permeability of the free space. Permeability of free space. So now a very interesting thing is going to develop. So right now we saw the equation over here. So the equation read our B naught was equal to, so I'll write down. So if I can write in terms of Bx, so same thing. So I'm only changing this denominations, nothing else. Same thing, I'll write I 2 pi r square into x. Okay, so this is the value, wherein our mu naught value I have written is equal to 4 into 10 power minus 7 Henry per meter, which is the permeability of the free space. So the differential flux, let d phi be the differential flux for a small region, small region of thickness dx. As we have seen, we have taken a small region, and let's suppose the length of that region is and 1 meter length of the conductor. Now this we know that our flux, okay, your flux by area is basically what? Current density. That this is B is equal to flux by area. Current density is equal to, sorry, magnetic field density, that is magnetic density. Current density J is equal to I by area. So this is magnetic density, this is current density. So now let's go for this. So d phi x would be equal to bx into dx, and the length I have taken over here is 1. L is equal to 1. So I can straight away write mu naught I, so that 2 pi r square, and for x I'll integrate x and dx. So I get this particular value because length is 1 meter. Now what I have to do is that the flux d phi x links only the fraction of the conductor from the center to radius x. Thus an assumption of uniform current density, that is, thus on assumption of uniform current density, so only the fraction. So what we see is that this flux d phi x, it only links where, if we see, and only on the assumption this flux links only on the, sorry, only on the fraction of conductor from the center, from the center to, to the radius, yeah, nice, radius x. So now what we see is that this, and this is the assumption that it is having a uniform current density, and we have this assumption. So it will link only the fraction. So please pay attention. It will link only the fraction. That is, the fraction would be what? Fraction that would be pi x square divided by pi r square, because it's linking, okay, of the total current is linked by the, so that means this, if you have to calculate the total current linkage, it will not link the entire conductor, so it only links for the fraction, that is x square by r square divided by d phi x. Now if you want to calculate the d phi x value is here for you, then substitute here. This would be x square r square into mu naught I 2 pi r square x dx. Now if you are calculating this value, so you get a value, so you get it in terms of mu naught I, instead of x it will become x cube dx 2 pi r4. So the total flux linkage is found by how? So now this is d phi x, so the total flux linkage will be found by integrating it from where? So you have to integrate this equation to find the total flux. Now the total flux should be found by integrating this region from where to where. So if you will go to the earlier circle which I have drawn over here, so the first circle, if yeah, so this is down there, I think, yeah, okay, so yeah, here, so you will see the flux linkage would be from 0 to r. So again you have to go from 0 to r, so the flux linkage over here would be from this direction to 0 to r. So you have to be sure, like when you are doing this, so you have to link the flux from 0 to r. So from 0 to r you have to link this, then only you will get. So once you are linking this from 0 to r, so the total flux, then you get what? You get internal flux linkage. So if you are linking it from 0 to r, so again integrating this, mu naught I 2 pi r4 will come out, mu naught I 2 pi r times 4 comes out, and only thing that 0 to r, x cube dx remains, so integrate this becomes x4. So again, so you are left with mu naught I 2 2 pi r4, and this becomes x2 will become x4 by 4 integration, and this is 0 to r. Now if you substitute this value, okay, if you substitute this value over here, let me rub something so that yeah, in this very, so I'm taking from here only, in this page, please follow this. If you substitute this mu naught I 2 pi r4, this becomes r4 by 4, so this will become mu naught I, this r4 and r4 will cancel, mu naught I by 8 pi, if I am not mistaken it should be mu naught I by 8 pi. So this is the expression, and this is in Weber per meter, so this is the expression that you are getting, mu naught I by 8 pi. So the expression that you got is mu naught I by 8 pi is for the leakage, uh, this is the flux that is the total flux linkages. So this is the flux linkage, it's not for the total inductance, this is for the flux linkage. Now if you have seen your, see, your flux linkage would be equal to inductance, internal inductance into total current. So if you have to calculate the current, so current would be flux linkage, so your inductance would be flux linkage divided by current. So here if you have to get the L internal, so it would be mu naught I divided by 8 pi divided by I, obviously. So this becomes mu naught I 8 pi into 1 by I. So this I cancels. So here we are left with mu naught by 8 pi. If you are not mistaken, so this value of mu naught for this L internal, if you have to calculate, this is nothing but as L internal. So you see that L internal value over here would be mu naught is 4 pi in 10 power minus 7, and here you have 8 pi. So this becomes 1 by 2 into 10 power minus 7. It's a dimensionless quantity. This is Henry per meter. The unit of inductance is Henry per meter, or millihenry per kilometer. So please pay attention. Unit of inductance would be in two types. Either it would be millihenry per kilometer or Henry per meter. So you are noting a very significant thing, that inductance that internal inductance that you calculated is half into 10 power minus 7. So note that this L internal is independent of the conductor radius. So nota bene, this is a very important point, that the internal inductance is independent. Internal inductance is independent of what? Dependent of the conductor radius. This is a very important point over here. So let's move to the external inductance calculations, and how do we go about the calculations of the L external. So this is like was for the internal inductance calculations. Now let's move to the external inductance calculations. So now on the same note, like we did for the internal inductance calculations, so similar pattern if we will be following for the external inductance. So we will get, so how we went around the internal inductance, same way we'll be seeing the external inductance calculations. In order to calculate the external inductance, we need to like take into account the other factors. So if you people are very new to the channel and I'm thinking that you are getting very bored, so let me stop this video over here, and let you people like, share and subscribe. We'll be back to the external inductance calculations, and again we'll be then total inductance, and then we'll start with the transmission line explanation. Thank you very much.